Right now, you are falling through a cosmic void 2 billion light-years across. Scientists confirmed this in 2013, but most people still don't know. We inhabit the KBS void, a cosmic desert where matter is thinned by 20%. This emptiness distorts our understanding of reality itself. Here, the universe seems to be expanding faster than anywhere else, violating our fundamental equations. Our journey will take us through a discovery that shook cosmology. We will understand why 90% of space is empty, and we will discover what it means to exist on the cosmic fringes. If you're ready to see the universe in a new way, click the like button and subscribe. Get ready. Here we go. 3 astronomers were counting galaxies when they noticed something impossible. Ryan Keenan, Amy Barger, and Lennox Cowie had studied 35,000 galaxies in 2013, mapping their locations across billions of light-years. The numbers didn't add up. Everywhere they looked near Earth, there were fewer galaxies than they should have been. Not just a little, but 20% fewer. This pattern extended in all directions for 1 billion light-years, forming a sphere of cosmic emptiness with us at the center. This wasn't a small gap between galaxy clusters. This was a void on a scale that, according to standard cosmology, shouldn't exist. The researchers triple-checked their data, used multiple galaxy surveys, and studied the sky from different angles. The result remained consistent. Our galaxy and everything around it resides within an extremely massive bubble of tenuous space, surpassing anything we've ever observed. The discovery has been given the almost mundane-sounding name of the KBS void, after the first letters of the 3 discoverers' names, but there's nothing mundane about it. In the standard model of cosmology, the universe should be roughly uniform if you look far enough away. Of course, galaxies clump together and leave empty spaces between them. This is expected. But such a vast region with such a significant matter deficit is beyond what can be explained by chance. Computer simulations of the evolution of the universe after the Big Bang rarely produce such large and empty voids. When they do occur, they require exceptionally rare initial conditions. The statistical probability is less than 1 in 1,000. Some scientists have calculated that this would require a deviation of 10 sigma from the average density. This means the probability is so small that a single such void might not be found in the entire observable universe. And yet, we live inside one. The consequences began cascading immediately. If we are in such an unusual place, aren't all our measurements distorted? When we point our telescopes at distant supernovae to measure the expansion rate of the universe, are we seeing the true cosmic expansion rate or a distorted local version? The void hypothesis offers an answer to one of the greatest mysteries of modern cosmology, the Hubble tension. For years, scientists measured 2 different expansion rates, depending on whether they were looking at the ancient universe or the nearby one. The figures differ by 9%. This doesn't seem like much, but it represents a crisis. Both measurements are extremely precise. Both should give the same answer. But they don't. If Earth is located inside a massive, tenuous region, the gravity of the denser matter surrounding the void will pull on the galaxies within it. This would add extra speed to their movement away from us, making the local expansion faster than average. Suddenly, the conflicting measurements made sense. We weren't measuring the universe incorrectly. We were measuring it from within the void. This realization changed everything. But it also raised an awkward question that cosmologists still wrestle with. If our location is so unusual, can we trust anything we think we know about the cosmos? What follows reveals just how strange our cosmic neighbor really is. Cosmic voids aren't actually completely empty, making them even stranger than their name suggests. Between these lonely galaxies stretches a vast expanse of space containing mostly dark matter, dark energy, and sparse wisps of hydrogen gas. The density is so low that gravity barely acts. Without sufficient mass to attract objects, structure formation effectively stops. New galaxy clusters cannot form. Rich superclusters do not emerge. The void remains a void. This emptiness has consequences that extend to physics itself. Gravity is already the weakest fundamental force in nature, requiring enormous masses, like planets and stars, to exert noticeable effects. In the void, where matter is sparse, gravity becomes even less significant. Dark energy, a mysterious pressure accelerating cosmic expansion, becomes the dominant force. In dense regions full of galaxies, gravity competes with dark energy, slowing the expansion in these areas. Within voids, gravity loses this battle. Dark energy wins decisively. As a result, voids expand faster than the rest of the universe. They grow like bubbles, expanding their boundaries, while the filaments of galaxies around them act as walls. This creates a self-sustaining cycle. The more a void expands, the emptier it becomes, allowing for even faster expansion. Scientists confirmed this through careful observations. They measured the motion of galaxies at the edges of voids compared to galaxies in denser regions. The void galaxies are rapidly moving away from the center, faster than cosmic expansion alone would explain. Something is pushing them outward. That something is the gravitational pull of all the matter outside the void. Think of the void as a valley surrounded by mountains. Gravity pulls down from the mountains into the valley. But since we're talking about space, not terrain, this pull causes galaxies to fall outward rather than inward. The effect is measurable and significant. Our own galaxy is moving away from the local void at 600,000 miles per hour. Driven by this gravitational imbalance, the void's interior becomes a strange place for physics. Light traveling through it experiences a smaller gravitational influence than light traveling through ordinary space. This subtly influences observations. When astronomers study the cosmic microwave background, CMB, the faint afterglow of the Big Bang, they notice that light passing through voids appears slightly cooler. The reduced gravity in voids causes a smaller gravitational redshift, which appears as cold spots on temperature maps of the early universe. These cold spots align perfectly with the locations where we observe large voids today. This coincidence is no coincidence. It's physics. Understanding what makes voids empty helps explain why they are so important to cosmology. They aren't just boring empty spaces between interesting galaxy clusters. They are laboratories where dark energy dominates and gravity fades into the background. By studying how matter behaves differently in voids compared to dense regions, scientists can test fundamental theories about how the universe works. The KBS void around us can be unsettling because it makes us question our cosmic typicality, but it also offers a rare opportunity. We are in the perfect position to study the most extreme low-density environments in the universe. The structure containing these voids is far stranger than anyone could have imagined. The universe is not a smooth soup of evenly distributed galaxies. Instead, it resembles Swiss cheese, where dense matter forms walls and filaments surrounding vast voids. This foamy architecture is called the cosmic web and is the largest structure in nature. Clusters of galaxies concentrate at intersections where multiple filaments meet, creating knots of intense matter density. These knots glow brightly with millions of galaxies packed relatively closely together. Between them run filaments, long chains of galaxy groups that can stretch for hundreds of millions of light years. These filaments form walls, vast sheets where galaxies gather in higher than average concentrations. Between the filaments and walls lie voids, occupying most of the volume, but containing almost no mass. This structure wasn't always obvious. For decades, astronomers photographed the sky and counted galaxies. But the true three-dimensional arrangement remained hidden. Distance measurements were poor. Galaxies that appeared close together could actually be separated by billions of light years, with one much farther away than the other. It wasn't until scientists began systematically measuring the redshifts of galaxies in the 1970s and 1980s that the cosmic web was revealed. Redshift surveys allowed astronomers to calculate the distance to each galaxy by measuring how much the expansion of space had stretched its light toward redder wavelengths. Suddenly, the distribution became clear. The universe had structure on scales no one expected. The first major void discovery occurred in 1978, when two independent teams discovered large, sparse regions. More surveys followed, each mapping farther into space and revealing an increasingly complex web. The Sloan Digital Sky Survey, launched in 2000, has created spectacular 3D maps spanning billions of light-years. These maps reveal the cosmic web in stunning detail. Filaments twist and branch like blood vessels. Voids appear as dark bubbles, sometimes 500 million light-years in diameter. The largest structures include the Sloan Great Wall, a filament nearly 1.5 billion light-years long. At the opposite end of the spectrum, supervoids like the Herodes void stretch 1.88 billion light-years across, with even fewer galaxies than the KBS void. Together, these features paint a picture of a universe organized on scales far larger than anyone predicted. Galaxies are not fundamental building blocks. The web itself is the structure, and galaxies merely mark places where matter is randomly concentrated. Why is the universe organized this way? The answer goes back to the very beginning. Immediately after the Big Bang, matter was not perfectly uniform. Quantum fluctuations in the first fraction of a second of the universe's existence created tiny variations in density. Some regions were slightly denser than average, others slightly less dense. These differences were tiny, perhaps 1 part in 100,000, but gravity amplifies even tiny advantages. Denser regions attracted more matter, becoming even denser. Less dense regions lost matter to their surroundings, becoming empty. Over hundreds of millions of years, this process moved forward like a growing avalanche. Small clumps merged into larger ones, which merged into galaxy clusters, which then formed filaments. Meanwhile, sparse regions expanded into voids. The cosmic web is essentially gravity at work over cosmic time, transforming barely perceptible initial ripples into the most grandiose architecture in existence. Today, voids occupy approximately 90% of the volume of space. Filaments and clusters make up the remaining 10%, but contain the majority of the mass. This imbalance determines the nature of the universe. We live not in a cosmos filled with galaxies, but in a cosmos of emptiness, interrupted by random concentrations of matter. The KBS void is just one bubble in this foam, but it's our bubble, and that has enormous implications for what we observe and how we interpret the universe. The next chapter will reveal exactly where we are in this vast void. The Milky Way isn't at the center of the KBS void, but it's close enough to matter. Measurements place our galaxy somewhere between 200 and 400 million light-years from the void's actual center. This may seem like a vast distance, and it is compared to anything humans experience, but the void extends 1 billion light-years in all directions from its center, making our displacement relatively small. We exist within a tenuous region, surrounded by the void's low-density medium in all directions. This situation is no accident. It has implications for every observation we make and every conclusion we draw about cosmology. If we were located entirely outside the void, in one of the dense filaments, our measurements of the expansion of the universe would look completely different. We would calculate a lower expansion rate, and the Hubble stress would not exist. Our larger cosmic neighborhood adds another layer to the story. The Milky Way belongs to the local group, a cluster of approximately 80 galaxies, including our giant neighbor Andromeda. The local group itself is located in the Laniakea supercluster, a massive structure containing approximately 100,000 galaxies spread over 520 million light-years. Laniakea is enormous by any standard. But even this supercluster lies within the KBS void. Consider this for a moment. A structure containing 100,000 galaxies is still considered part of a tenuous region. The void is so vast that it could swallow entire superclusters and still have space to spare. Laniakea is part of a sparse population of matter scattered throughout the void, one of the rare concentrations in otherwise barren space. The local group is also affected by another nearby void, called the local void, which is distinct from, but connected to the larger KBS void. The local void extends for approximately 200 million light-years and is located near our position. Our galaxy is moving away from it at 600,000 miles per hour, pushed by the gravitational pull of denser regions beyond. This motion is unrelated to the general cosmic expansion. It is called an intrinsic velocity, meaning it is the result of local gravitational effects, not the stretching of space itself. These intrinsic velocities complicate efforts to measure the true expansion rate, as they add additional motion on top of the expansion signal. Astronomers must carefully account for these local effects. But within the supervoid, these effects are amplified and more difficult to isolate. The void's influence extends even further. When scientists measure the motion of galaxies at distances up to 250 million light-years, they discover flows that exceed the predictions of standard cosmology. Entire regions of space move faster than they should, flowing in coherent patterns caused by the void's gravitational imbalance. The CBS void creates a large-scale velocity field that affects everything within it. Galaxies don't simply sit in an empty region, passively expanding with the universe. They actively respond to the gravitational landscape, accelerating outward from the rarefied region toward denser structures beyond the void's edge. This makes our local region of the universe more dynamic and unusual than the calm, uniform cosmos assumed by standard models. Our position within the void also affects what we can see. Light from distant galaxies travels through the void on its way to our telescopes. This light experiences a weaker gravitational interaction than light passing through denser regions. The reduced gravity creates subtle effects on the wavelength and energy of the light. Furthermore, the void itself influences the distribution of matter we observe. When we look outward from within the void, we see a shell of denser material surrounding us in all directions. This shell appears as a concentration of galaxy clusters and filaments at a certain range of distances. Beyond the shell, the universe returns to a more typical density. This creates an observational bias. We are not sampling from a random location in the universe. We're sampling one of its most extreme features. Living in the void means living with systematic uncertainty about how typical our measurements are. Every measurement of the universe's expansion rate you've ever heard could be wrong. Not because scientists made mistakes, but because we're measuring from within the cosmic void, which distorts the signal. The problem arises when astronomers use different methods to calculate the Hubble constant, a number that tells how quickly space is expanding. One method considers the cosmic microwave background, ancient light from when the universe was just 380,000 years old. This light carries information about the density and expansion rate of the early universe. Scientists input this data into cosmological models and calculate what the expansion velocity must be today. The answer is about 67 kilometers per second per megaparsec. This means that for every megaparsec of distance, approximately 3.3 million light-years, space expands at a rate of 67 kilometers per second. The second method considers nearby objects of known brightness, specifically type Ia supernovae and Cepheid stars. These objects serve as cosmic measuring sticks, as astronomers know exactly how bright they should be. By comparing their actual brightness with their apparent brightness as seen from Earth, scientists calculate their distance. Combining distance measurements with redshift measurements yields the expansion velocity directly. This local method consistently yields a higher figure, about 73 kilometers per second per megaparsec. The difference is 9%. Both measurements are extremely precise, with very small uncertainties. Both should yield the same answer if cosmology is correct. But they don't. This discrepancy is the Hubble intensity, and it has reached 5 sigma statistical significance, meaning the probability that it is simply a random variation is less than 1 in a million. The CBS void explains why these figures differ. When we measure the expansion velocity using nearby supernovae, we are measuring inside the void. The void's low density means less gravity, which slows the expansion. Matter from denser regions outside the void gravitationally attracts galaxies within it, adding additional outward velocity. Galaxies appear to be receding faster than in a typical region. This overestimates the local measurement of the Hubble constant. We're not measuring the true expansion rate of the universe. We're measuring the expansion rate plus the void's own velocity field. This effect is so large that it could explain most or all of the observed stress. When scientists model how a void as large and deep as the KBS would affect local measurements, they find that it could increase the apparent expansion rate just enough to match observations. But here's where things get awkward. If the void explains our local measurements, then those measurements, and those measurements, could be systematically distorted by our location. Some scientists resist this conclusion because it violates the cosmological principle, the assumption that Earth occupies no special position. The principle states that the universe should look roughly the same from any vantage point, if averaged over sufficiently large scales. Finding ourselves inside a supervoid that significantly influences our measurements seems at odds with this idea. It suggests we're in an unusual place, which makes physicists uncomfortable. Science has gradually stripped humanity of its special cosmic position. Earth is not the center of the solar system. The solar system is not the center of the galaxy. The galaxy is not the center of anything. And now we're expected to believe we're simply lucky to live inside one of the largest voids ever observed. The statistical improbability worries many researchers. However, the evidence continues to accumulate. The void exists. Our measurements are inconsistent. The void's effects correspond with observations. Whether we like the implications or not, the universe may actually be lying to us about its expansion rate. Or, more accurately, our location causes us to misinterpret what we measure. The crisis this creates in cosmology is deeper than most people realize. The Hubble tension is more than just an inconvenient discrepancy between two dimensions. It represents a fundamental challenge to our understanding of cosmic evolution. Cosmology is based on a framework called Lambda-CDM, or the Standard Model of Cosmology. This model is remarkably successful at explaining observations from a variety of sources. This explains temperature fluctuations in the cosmic microwave background, the abundance of light elements like hydrogen and helium, galaxy formation, and the large-scale structure of the universe. For decades, this was the accepted model because it worked so well in many contexts. However, the Hubble stress suggests that something is missing or wrong with this system. When model predictions disagree with observations at the 5 sigma level, scientists must take it seriously. This stress matters because the expansion rate determines everything else in cosmic history. If the universe expands faster, it will reach its current size in less time, becoming younger. Current calculations based on the cosmic microwave background radiation estimate the age of the universe at 13.8 billion years. But if the higher local value is correct globally, the universe may be as young as 12.7 billion years. This creates immediate problems. We observe stars in globular clusters that, according to stellar evolution models, are 13 billion years old. These stars would be older than the universe itself, which is impossible. Either our estimates of stellar ages are wrong, our understanding of stellar physics is flawed, or the higher Hubble constant is inapplicable to the early universe. None of these options are encouraging. The tension also affects our understanding of dark energy, the mysterious force accelerating cosmic expansion. According to standard models, dark energy makes up about 68% of the total energy content of the universe, but its properties depend sensitively on the expansion rate. If the expansion rate is higher than expected, the behavior of dark energy may differ from what current models predict. Some researchers have proposed that dark energy evolves over time rather than remaining constant, which would be revolutionary. Others believe we need to add new physics to our understanding of the early universe, perhaps even an additional burst of accelerated expansion shortly after the Big Bang. Each proposed solution introduces new complications and requires evidence that goes beyond simply correcting them. Hubble strain. Dozens of alternative explanations have been put forward. Some scientists suggest that the measurements themselves contain subtle systematic errors that have been missed. Perhaps dust between galaxies obscures supernovae more than previously accounted for, making them appear farther away and inflating the expansion rate. Or perhaps Cepheids behave differently in different environments, distorting their use as distance indicators. These explanations are constantly being tested and rejected as measurement techniques improve. The measurements are reliable. Other researchers propose modifications to Einstein's general theory of relativity. Perhaps gravity on cosmological scales acts somewhat differently than we think, which would change the predictions of expansion. This path leads into controversial territory, as general relativity has withstood all other tests. The void hypothesis offers a simpler solution, requiring fewer changes to fundamental physics. It simply states that we are in an unusual place, and our local measurements reflect this, rather than universal properties. This explanation is philosophically disturbing, but requires fewer assumptions than inventing new particles or altering gravity. Recent work has strengthened the void hypothesis, showing that it naturally predicts other observations. For example, the rate of outflow from the void should affect not only the expansion rate, but also the motion of galaxy clusters in our neighborhood. Measurements of these mass flows match the predictions of the void hypothesis. The hypothesis makes testable predictions that are confirmed. However, the debate continues. Not all cosmologists accept the void explanation. Some argue that even a void as large as the KBC cannot produce a strong enough effect to fully explain the stress. Others point out that such large supervoids should be rare, and our presence in one just when we have developed the precision to measure the Hubble constant seems suspicious. Perhaps we are somehow misinterpreting the data. The contradiction remains unresolved, so the Hubble tension continues to be called a crisis. It's not just a number that's different. It's a signal that our understanding of the cosmos may be incomplete. Understanding how gravity creates this disorder requires studying how forces act in empty space. Gravity inside empty space behaves counterintuitively. It pushes outward rather than pulls inward. This isn't because gravity itself is changing. The force of gravity always attracts mass to mass. But geometry matters. Imagine standing on a gentle slope surrounded by mountains. Gravity pulls you toward the mountains, which means it pushes you away from the center of the valley. Inside the cosmic void, galaxies experience the same effect. All matter resides outside the void, in surrounding filaments and clusters. This outer matter gravitationally attracts the inner material, pushing galaxies away from the void center and toward the denser regions beyond. The result is an outflow, a systematic stream of galaxies accelerating away from the region of lower density. This outflow is measurable and significant. Astronomers can track the velocities of galaxies using redshift measurements combined with distance estimates. When they map velocities around known voids, the picture becomes clear. Galaxies near the void centers are moving outward faster than predicted by cosmic expansion itself. The effect is strongest near the void center and weakens toward the edges, where the density of matter increases. For the specific KBC void, the outflow adds hundreds of kilometers per second to the velocities of galaxies within the void. Our own galaxy is involved in this process. The Milky Way is moving at 600,000 miles per hour away from the nearby local void, driven by a gravitational imbalance. This motion combines with other local effects, such as the gravitational pull of the Virgo cluster, to create an overall intrinsic velocity for our galaxy. The outflow has implications for measurements of cosmic expansion. When we observe distant galaxies and measure their redshifts, we see a combination of two effects: the expansion of space itself and the proper motion of the galaxies due to gravity. Scientists can usually separate these components because the proper velocities average out when considering large volumes. For every galaxy moving toward you due to local gravity, there's another galaxy moving away from you, and the average is zero. But inside the void, the proper velocities don't average out. They all point in the same direction, outward. This creates a systematic error that inflates the apparent expansion velocity when measured from inside the void. The problem is compounded at different distance scales. Close to the center of the void, the outflow is fast. Further from the center, but still within the void, the outflow is slower. Beyond the edge of the void, the proper velocities can even reverse as matter falls back toward denser filaments. This creates a complex velocity profile that varies with distance. When astronomers measure the Hubble constant using supernovae at different distances, they sample this changing velocity field. If most of their supernovae are located within a void, which is what happens since we deliberately avoid using extremely distant supernovae due to other complications, the measurement is enhanced by the outflow. The farther you measure, the less the void influences the result. This predicts that the Hubble constant should decrease with distance, and recent observations accurately confirm this trend. Modeling these effects requires careful calculations. Scientists need to estimate the size, depth, and density profile of the void, and then calculate the gravitational potential it creates. This potential determines how quickly material flows outward at each radius. Calculations show that a void with a radius of approximately 1 billion light-years and a density deficit of 20% could easily cause the observed velocity anomalies. The agreement between predictions and observations is so good that many researchers consider the explanation for the void convincing. However, the standard cosmological model has difficulty explaining how such a large void formed in the first place. Computer simulations based on the lambda CDM model rarely produce such extreme voids. When this happens, very specific initial conditions are required that are statistically unlikely. This raises a troubling possibility. Our cosmological model may be missing something important. If voids larger and deeper than expected continue to appear in observations, it's possible that structure formation works differently than standard theory predicts. Some scientists propose modified theories of gravity, where gravity is stronger on large scales, which would enhance structure formation and make large voids more common. Others suggest that the universe is simply more heterogeneous than expected, which would also make large voids less surprising. In any case, reverse gravity in voids tells us something important about cosmic evolution. Our motion in this gravitational landscape is faster than anyone expected. The Milky Way isn't standing still in space. It's hurtling through space at 600,000 miles per hour, roughly 850 times the speed of sound. This speed isn't driven by the expansion of space, but by local gravitational effects. Specifically, our galaxy is repelled by the local void and attracted to denser structures beyond it. This local void is distinct from, but connected to, the larger KBC void and strongly influences our motion. The void itself doesn't push us. Rather, the lack of matter in the void means that we are pulled toward it by a smaller gravitational force than by gravity pulling us in other directions. Denser regions win this tug-of-war, accelerating our galaxy away from the region of lower density. This speed is hard to comprehend. 600,000 miles per hour means the Milky Way travels approximately 167 meters every second. In 1 year, our galaxy travels about 5.2 billion miles through space, relatively empty. But even at this breakneck pace, the void is so vast that our motion barely matters. It would take hundreds of millions of years to cross it from one side to the other. Even at this speed, the void continues to expand due to cosmic expansion and dark energy, which grows faster than we can escape. We are inside the void now, and we will remain inside it for the foreseeable cosmological future. The local sheet adds another component to our motion. The local sheet is a flattened structure of galaxies, including the Milky Way, Andromeda, and other nearby galaxies. This sheet makes up one wall of the local void. The entire sheet is rushing away from the center of the void at a speed of about 260 kilometers per second, which is approximately 580,000 miles per hour. Our galaxy participates in this mass movement along with its neighbors. The sheet is not static. It's actively evacuating the void, flowing outward like water draining a depression. This movement has been going on for billions of years, and will continue for billions more. But there's more to our speed than simply escaping the void. The Milky Way is also falling into the Virgo cluster, a rich cluster of galaxies approximately 60 million light-years away. The Virgo cluster contains over 2,000 galaxies and possesses sufficient mass to gravitationally attract everything in the surrounding area, including us. This adds another component to our own velocity, approximately 250 kilometers per second, directed toward Virgo. Meanwhile, the Milky Way and Andromeda are gravitating toward each other and will collide in approximately 4 billion years. This motion adds another component to the velocity. When you add up all these gravitational effects, the Milky Way's overall proper velocity relative to the cosmic microwave background is about 627 kilometers per second. This is the velocity astronomers measure when they look at the dipole pattern in temperature. These motions are important because they complicate cosmological measurements. We need to correct for our own motion through space. Otherwise, galaxies in the direction of our motion appear blue-shifted, and those in the opposite direction appear red-shifted, creating a false picture mimicking cosmic structure. Astronomers have known about these corrections for decades and routinely apply them. But within the void, the corrections become more complex, as the void itself creates large-scale mass flows spanning hundreds of millions of light-years. Separating the void effect from true cosmic expansion requires careful modeling of the local velocity field. Our high speed in space is itself evidence of the existence of the void. If we lived in a typical region of moderate density, our own speed would be much lower, perhaps 1 or 2 kilometers per second at most. The fact that we are moving so fast indicates strong gravitational gradients in our vicinity, exactly what you would expect from being near a large region of reduced density. The velocity is consistent with the void hypothesis, and would be difficult to explain without it. This makes our motion a key piece of evidence in the debate over whether the KBC void exists, and whether it affects our measurements. The universe may lie to us about its expansion rate, but it can't hide the fact that we are hurtling through it at incredible speeds. This motion is linked to a deeper principle that the void fundamentally violates. The cosmological principle is one of the foundational assumptions of modern physics, and the KBC void threatens to undermine it. The principle states that the universe is homogeneous and isotropic on sufficiently large scales. Homogeneous means it is the same everywhere. No single place is special or different from any other when averaged over large regions. Isotropic means it's the same in all directions. The universe looks the same no matter which direction you look. These assumptions greatly simplify the mathematics of cosmology. They allow scientists to model the entire universe using relatively simple equations. Without the cosmological principle, the equations become much more complex, and predictions are much harder to make. The principle has been remarkably successful, accurately describing many observations. But the KBC void represents a serious violation of this homogeneity. If the void has a diameter of 2 billion light-years, with a density deficit of 20%, this represents a massive discontinuity. Even on cosmological scales, This void is not small compared to the observable universe. It constitutes a significant fraction of the volume within several billion light-years of Earth. More alarmingly, we happen to live near the center of this anomalous structure, which seems to contradict the idea that our location is unremarkable. Throughout history, science has consistently displaced Earth from any particular position. Copernicus demonstrated that Earth is not the center of the solar system. Subsequent observations have shown that the solar system is not the center of the galaxy, and the galaxy is not the center of anything. The cosmological principle is the ultimate expression of this tendency. Not only is the Earth not at the center, but there is no center at all, since every location is equivalent. The void challenges this worldview. If we live within an anomalously large region of reduced density, our location is by definition unusual. Voids are common in the universe, but most are smaller than the KBC void. Supervoids of this size are rare. Our presence in one raises questions about whether the cosmological principle truly applies, or whether it only applies approximately on scales significantly larger than previously assumed. Some scientists calculate that in a universe governed by standard cosmology, a void as large and deep as the KBC void should be extremely rare, perhaps with a statistical deviation of 10 sigma. In a typical, random realization of the universe's structure, you might not find one within the visible cosmos. However, we find one. This suggests either that we are incredibly lucky or that the standard model is wrong about structure formation. Defenders of the cosmological principle argue that the void doesn't actually violate the principle, since uniformity only applies on scales of a few hundred megaparsecs or more. The void has a diameter of about 600 megaparsecs, which is at the limit where uniformity should come into play. Perhaps the universe is less smooth on these scales than we assumed. Alternatively, perhaps the void isn't as extreme as measurements suggest. Different observational methods yield slightly different density contrasts for the void. If the true deficit is closer to 10 or 15% rather than 20, the statistical rarity becomes less severe. These counterarguments preserve the cosmological principle, but require accepting that our measurements are less precise than we thought. Another defense is that we shouldn't be surprised by being in an unusual location, since observers can only exist in certain types of environments. This is a weak anthropic explanation. Perhaps intelligent life requires the formation of galaxies, and galaxies form preferentially in moderately dense regions, not in the densest clusters or the emptiest voids. If most observers live in slightly sparse regions, then our existence in a small void isn't surprising. But this explanation only works if the KBC void isn't as extreme as it seems. A 20% deficit is more than slightly. It pushes the boundaries of what the anthropic principle can explain. The debate over the cosmological principle is unresolved. Some researchers believe the void is real and significant, requiring either modifications to cosmology or the acceptance of Earth's truly unusual position. Others believe the void is an observational artifact or is not as extreme as initially reported. Still others suggest the principle operates on even larger scales, and the apparent violation is temporary. Future observations should help resolve this question. Surveys mapping the universe at great distances and depths will reveal how rare large voids are compared to the predictions of standard models, or whether they are more common than expected. If large voids are found to be frequent, the cosmological principle will hold, but the standard model will require revision. If they are truly rare, we need to explain how we ended up in one. The origin of these voids goes back to the very first moments of the universe. The voids we observe today began as infinitesimally small quantum fluctuations in the first moments after the Big Bang. During a period called inflation, the universe expanded exponentially for a tiny fraction of a second, perhaps 10 to the negative 35th power of a second. During this expansion, quantum fluctuations stretched from subatomic to cosmic scales. These fluctuations created tiny variations in the density of matter and energy. In some regions, the density was slightly higher than average. In others, slightly lower. The variations were incredibly small, about 1 part in 100,000. But they were enough to lay the foundation for everything that followed. After inflation ended, the universe continued to expand, but much more slowly. Matter began to clump together under the influence of gravity, but gravitational attraction only amplified the initial differences in density. Regions that were initially slightly denser attracted more matter from their surroundings, making them even denser. This created a positive feedback loop. The denser a region became, the more it attracted matter. Over millions of years, these overdense regions contracted, forming the first stars, then galaxies, then galaxy clusters. Meanwhile, regions that were initially less dense lost matter to their denser neighbors. As matter flowed toward the contracting, overdense regions, the less dense regions became even emptier. These less dense regions evolved into voids. This process is called gravitational instability, and it transformed these tiny initial fluctuations into the grandiose large-scale structure we observe today. The cosmic microwave background radiation provides us with a snapshot of these density variations, when the universe was only 380,000 years old. At that time, these variations were still tiny, noticeable only as small temperature differences of about 100 millionths of a degree. However, these temperature differences directly correspond to differences in density. Warmer regions had slightly higher densities, while cooler regions had lower densities. Satellites such as the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck spacecraft have mapped these temperature variations across the sky with exceptional accuracy. The maps reveal a simulated pattern of hot and cold spots at various angular scales. This pattern contains the seeds of structure formation. Scientists can take this pattern and run it forward in computer simulations to predict what the structure should look like billions of years from now. These simulations reliably reproduce a cosmic web of filaments, clumps, and voids that closely resembles what we observe. The agreement between predictions and observations is one of the greatest achievements of modern cosmology. It confirms that our understanding of how gravity shapes structure over cosmic time is largely correct. However, simulations rarely produce voids as large or deep as the KBC void. This is where the tension arises. The initial quantum fluctuations were random, so each region had some probability of becoming a void or filament, but probability distributions matter. Small voids should be common. Medium-sized voids should be rarer. Extremely large voids should be very rare. The KBC void appears to be in the extremely rare category, raising questions about whether our simulations are missing something important. One possibility is that the initial quantum fluctuations were not entirely random, but had subtle patterns that favor the formation of large voids. This could have occurred if inflation did not smooth out the structure as uniformly as standard models predict. Another possibility is that gravity on large scales works somewhat differently than predicted by general relativity, which would alter the way voids form and evolve. A third possibility is that the universe simply has more structural diversity than cosmologists expected, making large voids less surprising. Each of these explanations requires further confirmation. Observations of more distant voids elsewhere in the universe would help determine how rare the KBC void truly is. If similar voids are discovered, it would indicate that the standard model underestimates structural variability. If they remain exceptionally rare, it would strengthen the case for modified physics or unusual initial conditions. The quantum origin of voids is both elegant and unsettling. It means that the cosmic desert we inhabit traces back to some molecular processes that occurred before the existence of atoms. Randomness on the smallest scales has propagated upward, creating structure on the largest scales. The organization of the universe is not deliberate or predetermined. This is a consequence of random quantum fluctuations, amplified by gravity over billions of years. This realization is one of the most profound insights of modern cosmology. But it also means that our position in this structure is the result of chance. There is no reason why we should have ended up in a void rather than a thread. We are here because the initial conditions in our region were slightly undersaturated. This randomness of quantum chance 14 billion years ago determines what we observe when we look at the cosmos today. The scale of these empty regions surpasses human imagination. When you imagine the universe, you probably picture a sky full of stars and galaxies. But reality is the opposite. The universe is overwhelmingly empty. Voids occupy approximately 90% of the total volume of space. Galaxies and galaxy clusters crowd the remaining 10%, packed into filaments and walls surrounding the voids. This isn't simply empty space in the sense of the vacuum between stars. It's void in the sense that entire regions spanning hundreds of millions of light-years contain almost no galaxies. If you could travel through the void, you'd travel for tens of millions of years at the speed of light without encountering a single galaxy. Isolation would be near absolute. This distribution creates an asymmetric universe. Most matter is concentrated in a small fraction of the volume. The filaments are densely populated by galaxies interacting, merging, and rapidly evolving. Star formation is active. Black holes grow, galaxies collide, and spark bursts of star formation. Meanwhile, silence reigns in the voids. A few lonely dwarf galaxies drift in the darkness, separated by vast distances. These void galaxies evolve slowly, because they rarely interact with their neighbors. They are typically smaller, dimmer, and less evolved than galaxies in denser regions. Star formation is sluggish. In many galaxies, the voids contain large amounts of neutral hydrogen gas that has not yet condensed into stars. They are galactic backwaters, isolated from the busy highways of the cosmic web. The extreme emptiness of the voids raises questions about just how empty space can truly be. Even in voids, dark matter is present. Dark matter makes up about 85% of all matter in the universe, but it doesn't interact with light, making it invisible to telescopes. It's detectable only through its gravitational influence. In voids, dark matter is much less concentrated than in filaments, but it still exists, accounting for about 15% of the average density of the universe. This may seem like a lot, but distributed across such vast volumes, the amount of dark matter per cubic light-year is incredibly small. Furthermore, voids contain dark energy, the mysterious component driving the acceleration of the universe. Dark energy appears to be uniformly distributed throughout space. Therefore, voids contain as much dark energy per unit volume as dense regions. In fact, since dark energy does not clump like matter, it becomes the dominant component in voids where matter is scarce. The interaction between dark matter and dark energy determines the evolution of voids. In the early universe, matter dominated even in undersaturated regions, and gravity still played a role. As the universe expanded and dark energy became more prominent, voids began to accelerate their expansion. This acceleration causes voids to grow faster over time, devouring the surrounding filaments. Ultimately, if dark energy continues to dominate, voids will consume an ever-increasing fraction of the universe. The filaments will thin out. Galaxy clusters will become isolated islands in an expanding ocean of emptiness. Billions of years from now, the universe will be even emptier than it is now, and voids will occupy an even larger fraction of the total volume. This future evolution is inevitable, given our understanding of dark energy. The universe is destined to become increasingly hollow. Understanding the fraction of voids in the universe is important for interpreting observations. When we measure average properties of the universe, such as the overall density of matter or the expansion rate, we average out both voids and filaments. If we fail to take into account the fact that most of space is empty, we may misinterpret the meaning of these averages. For example, measurements of the cosmic microwave background radiation yield an average matter density in the universe that is about 30% of the critical density needed to halt the expansion of the universe. But this average value includes both dense filaments and rare voids. The local density varies greatly depending on where you are. In a filament, the density can be 3 times higher than average. In a void, it's 15% of average. These variations matter when trying to understand local observations. The void fraction of 90% also influences searches for rare phenomena. For example, astronomers searching for distant supernovae or gamma-ray bursts are likely to find them in dense filaments, where star formation is active. Detecting these events in voids is much rarer, because voids contain fewer galaxies and less star formation. This creates an observational selection effect. Most interesting astronomical events occur in the busy 10% of the universe, not the quiet 90%. We study the universe from within active regions and largely ignore the empty ones. But voids are as much a part of cosmic reality as filaments. Understanding them is essential to understanding the universe as a whole. One void stands out as particularly impossible within existing physics. The KBC void defies probability in a way that deeply concerns cosmologists. Standard cosmology predicts that structures form through the gravitational collapse of initial density fluctuations. The larger and deeper the structure, the rarer it should be. Small voids spanning tens of millions of light-years are common, as they arise from ordinary small fluctuations. Large voids spanning hundreds of millions of light-years are rarer, as they require larger and rarer fluctuations. The KBC void is 2 billion light-years in diameter and is undersaturated by 20%. Computer simulations of structure formation using a cold dark matter model with a cosmological constant, lambda, rarely produce anything so extreme. When researchers run thousands of simulated universes and search for voids as large and deep as the KBC void, they find very few matches. The statistical probability of such a void existing is extremely low. Several studies have estimated its improbability. One analysis calculated that a void the size and depth of the KBC represents a deviation of 10 sigma from the expected density. In statistics, a 5 sigma result means the chance of chance is less than 1 in a million. A 10 sigma result is incredibly unlikely. You would have to observe trillions of universes to expect to find even one such void. And yet, we live in one of them. This is not a minor statistical anomaly. It is a huge red flag, indicating that either the observations or the model are flawed. If the observations are correct, as numerous independent studies indicate, then the model is missing something important. One possibility is that the initial density fluctuations after the Big Bang were not as smooth as predicted by standard inflation models. If inflation produced more energy on large scales than expected, large voids would have formed more easily. This would require a change in our understanding of inflation, which is already a speculative part of cosmology with limited direct confirmation. Another possibility is that structure formation occurred more rapidly or differently than predicted by standard models. If gravity was effectively stronger in the past, or if dark matter behaved differently than expected, structure would have formed more vigorously, creating larger voids and richer clusters. Some researchers propose modified theories of gravity, in which the strength of gravity varies depending on scale or environment. These theories may enhance structure formation and make large voids more likely. A third possibility is that the KBC void is not as extreme as measurements suggest. Perhaps observational biases or systematic errors in galaxy surveys have made the void appear deeper and larger than it actually is. Different groups using different data sets have measured the void's properties and obtained slightly different results. Some studies indicate a density deficit of 20%, while others suggest closer to 10 or 15%. If the true deficit is in the lower range, the statistical rarity becomes less severe. While this remains a challenge for standard models, confirming the precise properties of the void requires more data, particularly deeper galaxy surveys that can map the void's extent and density profile with greater precision. Future missions, such as the Euclid Space Telescope and the Vera Rubin Observatory, will provide much better data. The existence of the KBC void has become a focal point in debates about the standard cosmological model. Critics of cold dark matter with a cosmological constant point to the void as evidence that the model fails to account for large-scale phenomena. They argue that structure formation is poorly understood and that the standard model makes incorrect predictions. Defenders of the model counter that rare events do occur, and that finding oneself in a statistical outlier isn't impossible, just unlikely. They also note that other aspects of cosmology, such as the cosmic microwave background radiation, are very consistent with the predictions of the cold dark matter model with a cosmological constant. Rejecting the model or significantly modifying it based on a single anomalous structure seems premature. However, the void cannot be ignored. It is a real observation that requires explanation. Either we accept that we live in an exceptionally rare place, which violates the spirit of the cosmological principle, or we modify our models to make large voids more common, which requires changing fundamental assumptions about inflation, dark matter, or gravity. Neither option is satisfactory. Both represent significant shifts in our understanding of the universe. The KBC void has become a focal point of cosmological debate precisely because it lies at the intersection of observation and theory, challenging our most basic assumptions about how the universe works. Until this tension is resolved, the void remains a cosmic enigma that refuses to fit within our current understanding. These vast regions of emptiness serve an unexpected scientific purpose. Cosmic voids are the best places in the universe to study dark energy, as they are the only regions where dark energy completely dominates. In dense regions, such as galaxy clusters, gravity is strong enough to resist the expansion of the universe. Clusters hold themselves together gravitationally, despite the expansion of the universe around them. Even on somewhat larger scales and filaments, gravity remains relevant, slowing the expansion of space in these regions. But in voids, where matter is scarce, gravity becomes negligible. Without a significant gravitational force to counteract it, dark energy controls everything. Voids expand faster than the average rate of the universe, driven by the repulsive pressure of dark energy. This makes voids natural laboratories for measuring the strength and properties of dark energy. Dark energy is one of the most mysterious components of the universe. Discovered in 1998 through observations of distant supernovae, dark energy makes up approximately 68% of the total energy in the universe. It behaves in the opposite way to ordinary matter in gravity. Where gravity attracts objects, dark energy repels space, accelerating the expansion of the universe. The precise nature of dark energy remains unknown. It may be a cosmological constant, an unchanging energy density embedded in the very fabric of space. Or it could be a dynamic field whose strength varies in time and space. Distinguishing between these possibilities requires precise measurements of how the expansion accelerates under different conditions and at different points in cosmic history. Voids provide a clearer signal for these measurements than dense regions. In dense regions, gravity complicates matters. The local gravitational force from nearby masses influences the motion of galaxies, making it difficult to separate cosmic expansion from local effects. In voids, these complications are minimal. Galaxies move almost exclusively due to cosmic expansion and dark energy. By measuring how quickly voids expand compared to predictions, scientists can test whether dark energy behaves as a constant or varies. If dark energy is stronger in voids than elsewhere, or if it was different in the past, this will manifest as deviations from the expected rate of expansion of voids. Another way voids contribute is through their shape. Dark energy affects not only the rate of expansion of the universe, but also how it expands in different directions. If dark energy is truly uniform, voids should expand equally in all directions, remaining spherical. But if dark energy varies, or if other unknown forces exist, the voids could expand more in some directions than others, becoming elongated or distorted. Observations of the void shapes could thus reveal whether dark energy is uniform or has structure. Current measurements show that most large voids are roughly spherical, supporting the idea that dark energy is uniform. However, the measurements are not yet precise enough to rule out small variations. Improved surveys in the coming years will provide much better shape measurements. The expansion history of the voids also contains information about dark energy. The voids have been growing for billions of years, and their current size reflects this entire history. By modeling how the void should grow over time, taking into account the various properties of dark energy, scientists can compare predictions with observations and constrain what dark energy must be. For example, if dark energy was weaker in the past and became stronger recently, the voids would grow slowly at first and then accelerate. If dark energy were constant, the void should grow at a constant, accelerating rate, determined by this constant value. Observing voids at different distances, representing different moments in the past, allows us to test these scenarios. One particularly useful method involves measuring the edges of the voids. The boundary between the void and the surrounding filament represents a transition zone where the density increases sharply. This boundary evolves over time as matter flows out of the void and accumulates in filaments. The sharpness and position of this edge depend on how quickly the void expands, which is determined by dark energy. By mapping the edges of voids at different cosmic moments and comparing them with simulations, researchers can deduce how dark energy influenced the growth of the voids. Early results suggest that dark energy has been roughly constant over the past several billion years, consistent with the simplest models. However, ongoing research is refining these results and looking for any deviations that might hint at more complex behavior. Studying dark energy through voids is an active area of research. Future surveys will discover and characterize thousands of voids at varying distances and sizes. Each void provides an independent measurement of the effects of dark energy. Combining multiple measurements will significantly improve our understanding. If the voids reveal that dark energy varies or has structure, this will revolutionize cosmology. Even confirming that dark energy is constant and uniform will be important, as it will rule out many alternative theories. In any case, voids are proving to be crucial tools for exploring one of the deepest mysteries of the universe. The KBC void, being the largest and closest supervoids, offers the best opportunity for detailed study. Its proximity allows for measurements that are impossible with distant voids. Galaxies forming in these cosmic deserts face unique challenges. Galaxies within cosmic voids grow in profound solitude. Unlike galaxies in dense clusters, which frequently interact with their neighbors, galaxies in voids evolve in isolation. This difference in environment shapes everything about them. Galaxies in voids are typically smaller and dimmer than galaxies in filaments. They have less mass, contain fewer stars, and less total matter. Many galaxies in voids are classified as dwarf galaxies, barely massive enough to hold their gas together against the outward pressure of star formation. Their isolation means they rarely experience the galaxy mergers that are common in dense regions. Mergers are the primary drivers of galaxy evolution, triggering bursts of star formation and feeding central black holes. Without mergers, void galaxies evolve more slowly and remain less evolved. The rate of star formation in void galaxies is typically lower than in cluster galaxies. But there's a twist. Although most void galaxies slowly form stars, a significant fraction of them are starburst galaxies, experiencing intense, short-lived periods of vigorous star formation. This seems counterintuitive given their gas content. Void galaxies are often unusually rich in gas, containing large reserves of neutral hydrogen that has not yet metabolized into stars. In dense environments, interactions with neighboring galaxies can expel gas or initiate star formation, depleting the gas supply. In voids, galaxies retain their gas longer. When star formation does occur, perhaps driven by internal processes rather than external interactions, sufficient fuel is available. The result is an intense starburst, rapidly devouring the gas before it returns to a quiescent state. The morphology of galaxies in voids also differs. Most are late-stage spiral or irregular galaxies, not ellipticals. Elliptical galaxies form primarily through mergers, which are rare in voids. Without mergers, galaxies retain their disk structures and spiral arms. Some void galaxies exhibit remarkably pristine morphologies, with smooth disk profiles and regular rotation patterns. They are unaffected by interactions or gravitational tides from neighboring galaxies. This makes them excellent laboratories for studying how galaxies evolve in quiet environments. Observations of void galaxies provide a baseline for comparison with the more chaotic evolution observed in dense regions. Dark matter halos around void galaxies are another intriguing feature. Dark matter dominates the mass of each galaxy, forming a halo extending far beyond visible stars. In voids, these halos are subject to less external gravitational influence. They remain more spherical and unperturbed compared to halos in clusters, which are often stretched and distorted by tidal forces from neighboring halos. The simpler structure of halos in voids makes them easier to model and study. However, the lowest mass halos in voids face a problem. Below a certain mass threshold, roughly corresponding to a circular velocity of 35 km per second, halos lack sufficient gravity to effectively retain gas. Star formation requires the gas to cool and collapse, which occurs more easily in deeper gravity wells. The smallest halos cannot form stars at all. This explains why the voids are not completely filled with tiny dwarf galaxies. Below a certain mass, halos exist but remain dark, containing only dark matter and no visible galaxies. One of the mysterious aspects of void galaxies is their chemical composition. Stars create heavy elements through nuclear fusion, and when they die, they eject these elements into space. Subsequent generations of stars incorporate these elements, gradually enriching the galaxy's overall chemical composition. This process is called chemical evolution. Galaxies in voids, with their slower rates of star formation, should have lower chemical enrichment compared to galaxies in dense regions. Observations support this to some extent. Galaxies in voids tend to have lower metallicities, meaning lower abundances of elements heavier than helium, but the difference is not as great as expected. Some void galaxies exhibit chemical compositions remarkably similar to galaxies in normal environments. This suggests that chemical evolution is more complex than simple models predict, possibly involving gas flows into and out of galaxies that redistribute elements. The evolution of void galaxies over cosmic time is an active area of research. Observing void galaxies at different distances, corresponding to different moments in the past, allows scientists to track how these galaxies have changed. Early results suggest that void galaxies were relatively stable, evolving gradually without the dramatic transformations typical of clusters. This stability makes them valuable for understanding the internal processes that drive galaxy evolution, without the complications of their surrounding environment. Future surveys with improved sensitivity will detect fainter void galaxies and trace their properties over billions of years of cosmic history. These observations will test whether our understanding of galaxy formation is complete, or whether void environments reveal processes we've missed. The gigantic structure containing all these disparate void galaxies is even more astonishing. The Linnea supercluster is a striking structure that redefines our understanding of our cosmic neighborhood. Discovered in 2014, Linnea contains approximately 100,000 galaxies spread over an area of 520 million light-years. Its name comes from the Hawaiian language and means immeasurable sky, aptly describing its scale. The Milky Way resides on the outskirts of Linnea, part of a vast cosmic catchment where galaxies flow toward a central gravitational pull called the Great Attractor. The entire structure moves in concert, bound by gravitational currents that exceed cosmic expansion at these scales. Imagine Linnea as a watershed, where matter flows down into the deepest gravitational valley. Only here, the landscape is the curvature of spacetime, not literal topography. Here's the paradox. Linnea, despite containing 100,000 galaxies, is entirely contained within the KBS void. How can a supercluster, one of the largest connected structures in the universe, exist within a region of reduced density? The answer lies in the definition of density. The KBS void has a reduced density compared to the cosmic average measured on very large scales. But it is not uniformly empty. It contains filaments, which contain clusters, which contain groups, which contain galaxies, which contain stars. Structure exists on every scale. The KBS void is defined primarily by the absence of rich superclusters and large galaxy clusters at its center. The edges of the void, where the density returns to normal, are hundreds of millions of light-years away. Within this vast volume, there's still plenty of matter, just not as much as should be on average. Linnea occupies a fraction of this volume. It's large compared to typical superclusters, but small compared to the void itself. The gravitational flows within Linnea provide some of the best evidence yet for how gravity organizes matter. By mapping the velocities of galaxies within and around the supercluster, astronomers have constructed a three-dimensional flow map showing how matter moves through space. Galaxies closer to the Great Attractor are falling toward it faster. Galaxies on the outskirts of Linnea are just beginning to feel its pull. These flows define the boundaries of Linnea. Everything moving toward the Great Attractor is considered part of the supercluster. Everything moving away from it belongs to neighboring structures. The unique velocity of the Milky Way points toward the Great Attractor, confirming that we are gravitationally bound to Linnea. But Linnea itself is falling towards something even larger. The Shapley supercluster, located approximately 650 million light-years away, is the most massive structure in our region of the universe. It contains tens of thousands of galaxies and exerts a gravitational pull sufficient to affect everything around it, including Linnea. The entire Linnea supercluster is moving toward Shapley at several hundred kilometers per second. This creates a hierarchy of flows. Galaxies flow toward the clusters. Clusters flow toward superclusters, and superclusters flow toward even larger attractors. The KBS void modifies these flows, adding an outward component. Galaxies simultaneously fall toward local attractors, such as the Great Attractor, and flow outward from the center of the void. This combination produces complex velocity patterns. Understanding the structure and motion of Linnea helps clarify our position in the KBS void. We are not located at the center of the void in complete isolation. We are offset from the center, located in a moderately dense region that nevertheless has a lower density compared to the cosmic average. Linnea represents a significant concentration of matter within the void. But this is not enough to eliminate the overall lower density of the void. The paradox is resolved when you understand that large-scale and small-scale structures coexist. The void describes average properties on scales of billions of light-years. Linnea describes local properties on scales of hundreds of millions of light-years. Both are real, and both have implications for various aspects of cosmology. The measurements that reveal all this rely on a cosmic ruler constructed from sound waves in the infant universe. Baryonic acoustic oscillations or frozen sound waves from the early universe, and they have become the most reliable ruler for measuring cosmic distances. In the first 380,000 years after the Big Bang, the universe was a hot plasma, where matter and radiation were bound together. Sound waves propagated through this plasma, creating density fluctuations. When the universe cooled enough for atoms to form, the sound waves froze in place. The distance these waves traveled before freezing left an imprint on the distribution of matter today. This distance is approximately 490 million light-years, and it manifests as a characteristic scale in galaxy clusters. Astronomers can measure this scale and use it as a standard ruler, because the physics that created it is well understood. This ruler works at any distance. Whether you look at nearby galaxies or galaxies billions of light-years away, the same characteristic scale manifests itself in their distribution. By comparing the apparent size of this scale at different distances, scientists can map how the universe has expanded over time. It's like placing identical meter rulers at different distances and measuring their appearance. If the universe's expansion is accelerating, distant rulers appear smaller than they should. If expansion is slowing, they appear larger. This method, called baryon acoustic oscillation analysis, has revolutionized distance measurements in cosmology. Unlike other methods, which rely on the brightness of objects, which can be affected by dust or other complications, the baryon acoustic oscillation scale is purely geometric. Using this technique, researchers have mapped the three-dimensional distribution of galaxies over billions of light-years. These maps reveal the cosmic web in unprecedented detail. They also reveal the void of the CBS. When scientists analyze the distribution of galaxies in our local region and compare it with the predictions of baryon acoustic oscillations, they discover a clear deficit. The void manifests itself as a region where the observed scale of a galaxy cluster differs from that predicted by distant measurements. This discrepancy is exactly what is expected if you are located within a region of reduced density. Baryon acoustic oscillations provide independent confirmation of the void's existence and quantify its depth and extent. The measurements are not simple. Mapping the distribution of galaxies requires massive surveys that observe hundreds of thousands of galaxies and measure the position and redshift of each one. Projects like the Sloan Digital Sky Survey and the Baryon Oscillation Spectroscopic Survey have spent years collecting this data. Processing it requires complex statistical analysis to extract the BO signal from the noise of random galaxy positions. The signal is subtle, typically only a few % stronger clustering at a characteristic scale compared to other scales. But modern surveys are sensitive enough to reliably detect it. The voids show redshifts that are slightly higher than expected for their distance using the BO ruler. This corresponds to an outgoing velocity adding to the cosmic expansion signal. Thus, baryon acoustic oscillation measurements provide further evidence of the void's existence and its influence on our observations. They show that the Hubble stress is not limited to supernova measurements, but is found in several independent methods. The accuracy of baryon acoustic oscillation measurements continues to improve thanks to new surveys. The Dark Energy Spectroscopic Instrument, which began operations in 2021, is mapping tens of millions of galaxies with unprecedented accuracy. These measurements will allow for a much more detailed mapping of the void structure and velocity field. In a few years, astronomers will know the properties of the void to an uncertainty of a few %. Such precision will either confirm the void as an explanation for the Hubble stress, or reveal additional complications requiring further theoretical development. In any case, baryon acoustic oscillations prove to be an indispensable tool for understanding our cosmic environment. The temperature of the universe itself reveals the fingerprint of the void. The cosmic microwave background radiation fills the entire universe with faint light left over from the Big Bang. Its temperature is remarkably uniform, 2.7 Kelvin, just above absolute zero. But this uniformity is not perfect. There are tiny temperature variations, typically just a few millionths of a degree in one direction from the other. These variations carry information about the structure of the early universe. Hot spots correspond to regions that were slightly denser. Cold spots correspond to regions that were slightly less dense. Satellites have mapped these temperature variations across the sky with great precision, revealing the seeds of structure formation. But the cosmic microwave background radiation also reveals something else. It reveals evidence of cosmic voids. Light from the cosmic microwave background radiation has traveled through 13.8 billion years of cosmic evolution to reach us. During this journey, it passes through structures formed along the way, including voids. When light enters a void, it experiences less gravitational attraction than in denser regions. This creates a measurable effect called the integrated Sachs-Wolf effect. When a photon falls into a slightly less dense region, it gains a tiny amount of energy from the gravitational potential. As it rises back up, it loses energy. Normally, these effects completely cancel out. But if the void expands as the photon passes through it, which happens due to dark energy, the cancellation is incomplete. The photon ends up with slightly less energy than it started with, which manifests as a drop in temperature. This effect is tiny but detectable when averaged over many voids. Astronomers located large voids in the nearby universe using galaxy surveys. They then looked at the temperature of the cosmic microwave background radiation in these directions and found that, on average, the temperature is 10 millionths of a degree lower than the average for the universe. The correlation is statistically significant and matches theoretical predictions. It confirms that voids influence the cosmic microwave background radiation through the integrated Sachs-Wolf effect. For the KBS void, in particular, the effect should be particularly strong due to its size. Light from the cosmic microwave background radiation passes through almost the entire void on its way to us, accumulating a temperature deficit over the entire billion light-years. One of the most intriguing features of the cosmic microwave background radiation is the cold spot, discovered by the Wilkinson Microwave Anisotropy Probe (WMAP) satellite. This region spans about 5 degrees on the sky and is about 100 millionths of a degree cooler than the surrounding regions. It is unusually large and cold compared to the typical fluctuations expected in the early universe. One explanation is that the cold spot is the result of a supervoid in this line of sight. If a particularly large and deep void is located in this direction, it could create the observed temperature deficit via the integrated Sachs-Wolf effect. Some researchers have searched for such a void in galaxy surveys and found weak evidence of decreased density in this region. However, the connection remains controversial, as the supervoid required to explain the cold spot is itself statistically unlikely. The CBS void does not coincide with the cold spot. It surrounds us in all directions, rather than appearing in one specific direction. Its temperature signature is therefore more subtle, appearing as a modification of the overall pattern of the cosmic microwave background radiation rather than a local anomaly. Detecting this signature requires careful modeling of what the cosmic microwave background radiation should look like with and without the void. Preliminary analyses suggest that the presence of the void is consistent with the observed cosmic microwave background radiation. However, the signal is not yet conclusive. Future measurements with greater sensitivity should clarify whether the void leaves a detectable imprint on the temperature distribution of the cosmic microwave background radiation. Temperature measurements also constrain the properties of the void. If the void were much deeper or larger than current estimates, it would create a stronger temperature signal, which should already be visible. The fact that there are no dramatic anomalies in the cosmic microwave background radiation in our direction places upper limits on the extremeness of the void. These limits are consistent with a 20% density deficit extending over approximately 1 billion light-years, consistent with other measurements. Thus, the cosmic microwave background radiation provides an independent test of the existence of the void and its properties. It's reassuring that several independent lines of evidence point to the same basic picture. We live in a large region of reduced density with significant, but not extreme, properties. The existence of the void has led some scientists to question the need to rethink gravity itself. The standard theory of gravity is Einstein's general theory of relativity, formulated in 1915. It has withstood every test it's been subjected to for over a century. From predicting the bending of light by massive objects to explaining the orbital decay of binary pulsars, general relativity forms the foundation of modern cosmology. But the CBS void challenges this foundation in unexpected ways. If the void is too large and too deep to arise naturally in simulations based on general relativity and lambda CDM, gravity may not work exactly as Einstein predicted on the largest scales. Some scientists propose modifying gravity rather than accepting that we live in a statistically improbable place. Modified Newtonian dynamics, or MOND, is the most well-known alternative theory of gravity, proposed in 1983 by physicist Maurice Milgros. MOND proposes that gravity behaves differently when accelerations are extremely small, below a certain threshold. At high accelerations, as on Earth or in the inner solar system, gravity precisely follows Newton's laws and Einstein's corrections. But at tiny accelerations, relevant at the outskirts of galaxies and on cosmological scales, gravity becomes stronger than predicted by general relativity. This modification was originally proposed to explain the rotation curves of galaxies without invoking dark matter. Galaxies rotate faster than visible matter can explain. Either there is invisible dark matter providing additional gravity, or gravity itself is stronger at large distances. MOND has struggled to explain many cosmological observations, but it performs better than expected in explaining some features of the cosmic web. In MOND cosmology, structures form more efficiently because enhanced gravity on large scales attracts matter more effectively. This leads to the formation of richer superclusters and deeper voids compared to standard gravity. Computer simulations using MOND gravity naturally create voids the size of the CBS void without the need for unusual initial conditions. Statistical improbability disappears. The void becomes an expected consequence of how structure forms under modified gravity. This is an attractive feature, as it resolves the discrepancy between observations and theory without resorting to extreme luck. However, MOND faces serious difficulties. It struggles to explain temperature fluctuations in the cosmic microwave background radiation, which standard cosmology explains perfectly well using general relativity. Even modified Newtonian dynamics, MOND, cannot easily explain observations of gravitational lensing, where massive galaxy clusters bend light from background galaxies. The observed distortion requires more gravity than visible matter. Furthermore, MOND may still require dark matter. Some researchers have developed hybrid models that combine MOND with a small amount of dark matter, typically in the form of neutrinos. These models, called hot dark matter neutrino cosmologies, can explain both the cosmic microwave background and the enhanced structure formation observed in the cosmic web. Another class of modified gravity theories involves altering the way gravity propagates over large distances, rather than changing its strength. These theories, collectively called modified gravity theories, introduce additional fields or higher dimensional effects that alter gravitational dynamics on cosmological scales, while preserving the properties of general relativity on smaller scales. Some of these theories predict that gravity becomes effectively stronger in low-density regions such as voids, facilitating the formation of large voids. Testing these theories requires precise measurements of how matter moves in voids compared to dense regions. If velocity patterns deviate from the predictions of general relativity, this may indicate the presence of modified gravity. The debate between modified gravity and standard cosmology, with its statistically unlikely void, remains unresolved. Proponents of modified gravity argue that the repeated detection of structures that are too large or too rare for standard models indicates that the models are flawed. They cite the KBC void, the Chapel supercluster, the Sloan Great Wall, and other enormous structures as evidence that structure formation is more energetic than predicted by Landolt dark matter. Defenders of standard cosmology argue that modified gravity theories have their own problems, and that using them to solve one puzzle often creates new puzzles elsewhere. They prefer to accept that we live in an unusual place rather than challenge a century of successful gravitational physics. Future observations should help resolve this debate. If large voids and extreme structures prove more common than currently believed, modified gravity will become more attractive. If they remain rare, the standard model will survive, but leave us with the uncomfortable conclusion that Earth occupies a special place. In any case, the KBC void has become a battleground on which fundamental physics is being tested. The existence of the void threatens our calculations of the age of the universe. The age of the universe is one of the most important figures in cosmology, and the KBC void threatens it. Current measurements based on the cosmic microwave background, CMB, place the age of the universe at 13,800,000,000 years. This figure is derived from detailed models of how the universe expanded from the Big Bang to the present. The models use the cosmic expansion rate measured from the CMB, along with other parameters such as the density of matter and the density of dark energy. Together, these parameters determine how long ago the Big Bang occurred. This result has been verified by several independent analyses and is considered highly reliable. But if the local expansion rate is indeed higher than the cosmic average due to the void, these models could be wrong. Here's the problem. If the locally measured Hubble constant, approximately 73 kilometers per second per megaparsec, represents the true expansion rate of the universe, and not a distorted local value due to the void, then the universe has been expanding faster throughout its history. A higher expansion rate means the universe reached its current size in a shorter time. Calculations show that this would make the universe about 8% younger, approximately 12,700,000,000 years old, rather than 13,800,000,000 years old. This may seem like a small difference, but it creates serious contradictions with other observations. The oldest stars in globular clusters appear to be approximately 13 billion years old, based on the theory of stellar evolution. No stars can be older than the universe itself. This conflict has led to intensive study of stellar age measurements. Age is determined by understanding how stars evolve over time. Stars of different masses burn through their nuclear fuel at different rates. Low-mass stars live for hundreds of billions of years. High-mass stars exhaust themselves in just millions of years. By observing which stars in a globular cluster have reached the end of their lives, astronomers can estimate when all the stars in that cluster formed. The oldest clusters show that their most massive remaining stars are barely alive, indicating that the clusters formed around 13 billion years ago. These measurements depend on an understanding of stellar physics, which is well tested but not perfect. Small uncertainties in how stars burn hydrogen or how they evolve from the main sequence can shift age estimates by hundreds of millions of years. Some researchers argue that if stellar ages are sufficiently uncertain, they may correspond to a younger universe. Perhaps globular clusters are actually 12,500,000,000 years old, rather than 13 billion years, which would correspond to a younger universe. But this requires assuming that current stellar models are systematically wrong in precisely the right direction, which seems far-fetched. Other scientists point out that stellar ages aren't the only constraint. The cooling time of white dwarfs provides an independent age measurement. White dwarfs are the remnants of dead stars, slowly cooling over billions of years. The coldest white dwarfs we observe have been cooling for approximately 12 to 13 billion years, again suggesting that the universe is at least that old. These measurements are independent of stellar evolution models, making them difficult to correct. The age conflict, like the Hubble constant conflict, can be resolved if the local expansion rate doesn't reflect the global average. If the void inflates our local measurements, the 13.8 billion year estimate for the cosmic microwave background radiation may be correct. After all, the universe would be old enough for observable stars and white dwarfs to exist. This solution requires accepting that we live in an unusual location, which philosophically troubles some scientists, but it avoids the need for major changes to stellar physics or cosmology. Alternatively, both measurements could be partially correct if dark energy has evolved over time. If dark energy was weaker in the past and has become stronger recently, the early expansion would have been slower, and the universe would be older than the high local Hubble constant suggests. This scenario is speculative, but not impossible. The age problem highlights a more general problem in cosmology. Many of the parameters we measure are interrelated. Changing the expansion rate affects not only the age of the universe, but also the density of matter, the properties of dark energy, and predictions of structure formation. You can't adjust one parameter without affecting others. This makes conflict resolution difficult, since corrections in one area often create problems in another. The KBC void offers a way to preserve much of the standard model by attributing discrepancies to our unusual location, but it doesn't resolve the age conflict entirely, since some evidence for the age of the universe comes from objects within the void itself. These local age measurements should be independent of the void's influence on expansion measurements. However, they are closer to the age determined from the cosmic microwave background than to the age determined from the local Hubble constant. This internal consistency suggests that the void explanation, while attractive, may be incomplete. Ancient starlight poses another challenge for void-based solutions. The oldest stars in our galaxy pose a stubborn problem for any cosmological model that makes the universe significantly younger. These ancient stars, found primarily in globular clusters and galactic halos, contain very little metal. In astronomy, a metal means any element heavier than helium. The first stars in the universe formed from pure hydrogen and helium left over from the Big Bang. They created heavier elements through thermonuclear fusion and dispersed them into space when they died. Subsequent generations of stars incorporated these metals, gradually increasing the metallicity of the galaxy. The metal-poorest stars we observe today must have formed very early, before significant metal enrichment occurred. Their age directly tells us how long ago the galaxy formed. Measuring the age of stars requires an understanding of stellar structure and evolution. Stars spend most of their lives burning hydrogen in their cores, a phase called the main sequence. The time a star spends on the main sequence depends on its mass. Massive stars burn through their fuel quickly, while low-mass stars burn through it slowly. When a star exhausts the hydrogen in its core, it evolves off the main sequence, expanding into a red giant and undergoing further evolutionary stages. By observing a cluster of stars born simultaneously, astronomers can see which masses have evolved off the main sequence. This turning point reveals the age of the cluster. The dimmest stars, still on the main sequence, indicate how long hydrogen burning has been going on, directly measuring the time since formation. The ages of globular clusters obtained in this way are consistently around 12.5 to 13 billion years old. The uncertainty is several hundred million years, largely due to uncertainties in stellar physics, such as the efficiency of mixing of stars' internal material or the amount of mass they lose through stellar winds. However, the measurements are consistent for many clusters using different methods. The Gaia space mission revolutionized these measurements, providing precise distances to globular clusters through parallax measurements. Knowing the precise distance allows us to determine the absolute brightness, eliminating one major uncertainty in age calculations. Improved measurements confirm that the oldest clusters are indeed around 13 billion years old. This poses a problem if the universe is only 12 billion, 700 million years old. As the high local Hubble constant suggests, you can't fit 13 billion-year-old stars into a universe that's 12 billion, 700 million years old. The numbers simply don't add up. Some solution is required. Either the stellar ages are wrong, or the age of the universe is wrong, or both are partially wrong in compensating ways. Measurements of stellar ages are reliable enough that large errors seem unlikely. They are based on well-established physics and confirmed by a variety of methods. The age of the universe based on the cosmic microwave background is also reliable and depends on a completely different set of physics. This leaves the high local Hubble constant as the most likely culprit. If this measurement is inflated due to the void, the contradiction disappears. However, the situation is more complex. The oldest stars are local objects within the Milky Way. If the KBC void significantly affects our measurements of the properties of the universe, shouldn't it also affect our interpretation of these stars? Some researchers argue against it, because stellar ages depend on local physics, such as nuclear reaction rates, and not on cosmic expansion. A star's age is determined by how long it burns hydrogen, which is unaffected by whether we live in a void. Other researchers counter that the initial conditions for star formation in our galaxy depend on when the galaxy formed, which depends on cosmic history. If the void influenced the formation of structures in our region, the first stars could have formed earlier or later than in typical regions. This debate touches on a fundamental question: how much does our local environment influence local observations compared to cosmic observations? Measurements of distant supernovae and expansion rates are clearly affected by the void, as they involve light traveling through the void and the unusual velocities within it. But measurements of objects within our galaxy should be largely unaffected, as they depend only on local physics. Thus, the age conflict may indicate that the high local Hubble constant is not simply a void effect, but a genuine global conflict requiring new physics. Alternatively, it may indicate that our understanding of stellar evolution needs to be refined. This question remains unresolved and will require further observations and theoretical work to clarify. The motion of galaxies over vast distances adds another complication. Galaxies are not static. They move through space under the gravitational pull of surrounding structures. These motions are called unusual velocities because they are intrinsic to each galaxy, distinct from the general cosmic expansion. In standard cosmology, unusual velocities should be relatively small and random on large scales. Nearby galaxies might move at a few hundred kilometers per second due to local gravity. But when averaging over volumes hundreds of millions of light-years in size, these unusual velocities should largely cancel out. The average motion, called the net flux, should be close to zero. This predicts homogeneity. If the universe is truly homogeneous on large scales, there should be no coherent large-scale flows, since there are no large-scale gravitational gradients to cause them. Observations tell a different story. Galaxy velocity measurements using several methods reveal significant common flows extending over distances of 200 to 300 million light-years. These flows reach speeds of 400 kilometers per second or more, much higher than predicted by standard cosmology. On such large scales, the flows are coherent, meaning that vast volumes of galaxies move in roughly the same direction. This suggests the presence of a large-scale structure producing gravitational gradients that pull matter in specific directions. The KBC void is precisely the structure that could produce such flows. Matter within the void is accelerated outward toward denser regions beyond the edges of the void. This creates a general flow directed away from the center of the void. Measuring the general flows is difficult because it requires precise distance estimates for many galaxies. Redshift alone is insufficient because it confounds cosmic expansion with the unusual velocity. Independent distance measurements, independent of redshift, are needed. Methods such as the Tully-Fisher relations for spiral galaxies and the fundamental plane relations for elliptical galaxies yield these distances by comparing the distance-based velocity with the redshift-based velocity. Astronomers can extract the unusual velocity. Compiling measurements for thousands of galaxies allows mapping the large-scale velocity field. The Cosmic Flows project has accomplished just that, creating the most detailed maps of net flows to date. The observed net flows match the predictions of models that include the KBC void. When researchers simulate how galaxies should move if they are located within a large underdensified region surrounded by overdensified shells, the predicted velocities and flow patterns closely match observations. The flows are strongest near the edges of the void, where the density gradient is steepest. They flow away from the underdensified region toward the surrounding filaments. The magnitude of the flows depends on the depth and size of the void. A 20% density deficit spread over 1 billion light-years results in flows of about 400 kilometers per second. This is precisely what is observed. This agreement is striking and provides strong support for the void hypothesis. Standard cosmology without a void has difficulty explaining these flows. Models based on lambda-like cold dark matter predict that the overall flows should decrease rapidly with scale. By the time you average over 200 million light-years, the overall flows should be less than 100 kilometers per second. The observed flows are 4 times greater. You can increase the predicted fluxes by assuming more structure than usual, but this requires inducing rare density fluctuations, which reintroduces the same problem of statistical improbability presented by the void. In any case, observations point to more structure on larger scales than standard models confidently predict. Some cosmologists view this as evidence that lambda-cold dark matter is missing something, either in its description of dark matter, dark energy, or the gravitational physics that govern structure formation. Alternative theories, such as modified gravity, naturally predict stronger overall fluxes because they enhance structure formation. For example, in Mond cosmology, the effective gravitational force is stronger on large scales, creating deeper potential wells and stronger flows. The observed net flows match the predictions without the need for statistically improbable structures. This has led some researchers to favor modified gravity as a more natural explanation for both the KBC void and the associated net flows. However, modified gravity has other difficulties, and so the debate continues. Upcoming surveys will measure net flows at even greater distances and with greater precision. If the flows remain strong beyond 300 million light-years, this will further challenge standard cosmology. If they decrease as expected, this would indicate that the KBC void is an isolated feature, not an indicator of systematic problems with the model. Observations of common flows highlight a theme that has emerged throughout this story. Our local cosmic environment is more dynamic and structured than simple, uniform models suggest. The universe on large scales may not be as smooth as the cosmological principle requires. Whether this means we live in an unusual place, or that our models need to be revised, depends on how these observations unfold. The KBC void and its associated flows are at the center of this evolving story. There is another, even larger void in the cosmos. The KBC void isn't the largest known underdensity region. That distinction belongs to the Eridanus supervoids, discovered by its influence on the cosmic microwave background. Located in the constellation Eridanus, this void has a diameter of approximately 1.8 billion light-years, making it slightly smaller than the KBC void but comparable in scale. What makes the Eridan supervoids particularly intriguing is how they were discovered. Astronomers didn't discover it by counting galaxies. They discovered it by noticing an unusually cold spot on the temperature map. This cold spot, about 10 degrees across, corresponds to a region where the cosmic microwave background is approximately 70 millionths of a degree cooler than average. This is much colder than typical fluctuations from the early universe. The cold spot, as it's called, was discovered by the WMAP spacecraft in 2005. Its existence puzzled cosmologists because its size and temperature deficit are statistically unusual. Random fluctuations from the early universe should occasionally produce cold spots, but such a large and cold spot is rare, occurring in only 2% of simulated universes. Some researchers initially proposed exotic explanations, including the possibility that it represented a collision between our universe and another universe in a multiverse. More prosaic explanations suggested it could have been a statistical quirk or a data processing artifact, but the cold spot persisted in several independent data sets, including observations from the Planck satellite. A more conventional explanation emerged when astronomers examined the distribution of galaxies in the direction of the cold spot. They found evidence of a large region of underdensity roughly aligned with it. This void, later named the Residing supervoids, is located approximately 3 billion light-years away. Light from the cosmic microwave background passes through this void on its way to Earth, experiencing the integrated Sachs-Wolf effect. As light passes through the expanding void, it loses energy, manifesting as a temperature deficit. Calculations show that a void the size and depth of the Residing supervoids can explain approximately half of the observed temperature anomaly in the cold spot. The other half may be due to a chance coincidence with a cold fluctuation in the cosmic microwave background. Alternatively, this may indicate that the void is much larger and deeper than current measurements suggest. The Residing supervoids raise the same questions as the KBC void. How did such a vast, low-density region form? Is it consistent with standard cosmology, or does it require unusual initial conditions? The void's existence was predicted by the cosmic microwave background cold spot even before it was confirmed by galaxy surveys, giving researchers some confidence in its reality. However, precisely determining its properties remains difficult due to its vast distance. Surveys of galaxies at this distance are less complete than those at nearby locations. Many faint galaxies are missed, making it difficult to quantify the precise density deficit. Current estimates indicate a deficit of approximately 20 to 30% compared to the cosmic average. Like the KBC void, if both the KBC void and the Residing supervoids are real, and as extreme as measurements suggest, this raises the possibility that such voids are more common than predicted by standard cosmology. Two large supervoids in the observable universe may still be compatible with a lambda-CDM model, given some statistical uncertainty. However, the discovery of 3 or 4 such objects will become increasingly difficult to explain. Future deep surveys will map the universe to even greater distances and discover more voids. The statistical distribution of void sizes and depths will allow us to verify whether structure formation matches predictions. If large voids are common, this suggests either that we misunderstand structure formation or that we live in an atypical region of the universe where large voids are randomly clustered. Neither option is encouraging. The Residing supervoid also demonstrates that voids measurably affect observations. The temperature deficit they create in the cosmic microwave background is small, but detectable. The velocity fields they generate are observed through measurements of the so-called mass flux. These effects are not simply theoretical predictions. They are real phenomena that astronomers can study. This gives researchers hope that the mysteries associated with the KBC void and the Hubble stress may eventually be resolved through improved observations. If voids systematically influence measurements in known ways, these effects can be corrected for or modeled. The challenge is to obtain sufficient data to accurately characterize the structure of voids in the universe. One thing is clear: the universe contains more large voids than early cosmological models predicted. Whether this reflects the rarity of our cosmic neighborhood or the limitations of our models remains an open question. Our measurements are only reliable when we look far beyond our local region. The term Hubble bubble has arisen to describe a disturbing pattern in observations. When astronomers measure the Hubble constant using nearby objects, such as supernovae, within approximately 2 billion light-years, they obtain higher values, around 73 kilometers per second per megaparsec. When they use objects further than 2 billion light-years away or rely on cosmic microwave background radiation data, they obtain lower values, around 67 kilometers per second per megaparsec. The boundary, approximately 2 billion light-years distant, is suspiciously close to the edge of the KBC void. This has led researchers to hypothesize that measurements within the void are affected by it, creating a bubble of distorted observations. Only by looking beyond this bubble can we see the true rate of expansion of the universe. This hypothesis makes a clear prediction. The measured Hubble constant should vary with distance. Nearby measurements should show the highest values. As you look further, approaching and crossing the edge of the void, the measured value should decrease to the cosmic average. Beyond 2 billion light-years, it should stabilize at a lower value. This is precisely what recent observations are beginning to show. Studies using supernovae at various distances show that the derived Hubble constant decreases with redshift. This trend is not yet definitive, as measuring distances to very distant supernovae is challenging, and the uncertainties are large. But the direction of the trend is consistent with the predictions of the Hubble bubble hypothesis. If the bubble is real, it poses a significant challenge for cosmology. Most measurements of the local expansion velocity inevitably use nearby objects, because only these can be observed with sufficient detail. Distant objects are dimmer and more difficult to accurately characterize. This means that our most reliable local measurements are precisely those most affected by the void. We're trapped inside a bubble, unable to step outside our local environment to see what the universe really looks like. It's like trying to determine Earth's climate by measuring only the temperature inside a heated building. You can make very precise measurements, but they don't reflect the global average. Breaking out of the bubble requires observing objects beyond 2 billion light-years with the same precision as nearby objects. This is technologically challenging, but it's becoming possible. Space telescopes, like the James Webb Space Telescope, can observe distant supernovae in unprecedented detail. Ground-based observatories, with enormous mirrors and advanced instruments, are detecting quasars and other bright objects at extreme distances. These distant probes offer a window into the universe beyond the bubble. Early results suggest that the distant universe is expanding at the rate predicted by the cosmic microwave background, consistent with the bubble hypothesis. However, data are still insufficient. Further observations are needed to confirm the trend and determine whether it fully resolves the Hubble tension. The bubble concept also applies to other dimensions. Observations of mass flows show significant motions out to approximately 300 million light-years, but appear to diminish at greater distances. This is consistent with the void creating a local velocity field that dissipates as we approach the edge of the void. Measurements of baryon acoustic oscillations show discrepancies primarily at low redshifts, again suggesting local effects. Multiple independent lines of evidence point to the same conclusion. Our local environment, within approximately 2 billion light-years, is systematically different from the universe as a whole. We live on an island of unusual properties, surrounded by a more typical cosmos. Accepting the Hubble bubble hypothesis means acknowledging that many of the measurements we use to understand the universe are distorted by our location. This is philosophically inconvenient. Scientists prefer to believe their observations are representative of universal truths, not local flukes. But evidence increasingly suggests that we cannot escape our local bias without looking far enough for the void's influence to weaken. Future surveys exploring the universe beyond 2 billion light-years will be crucial to confirm whether the bubble is real and whether it fully explains the Hubble stress. If so, cosmology can breathe a sigh of relief. The standard model works perfectly. We were just lucky to measure from a strange place. If the stress persists even at great distances, new physics will be required. The void does more than simply distort measurements. It affects the very possibility of structure formation within it. Cosmic voids act as filters, preventing the formation of certain types of structures within them. In dense regions of the cosmic web, galaxies frequently collide and merge. Small galaxies merge into larger ones. Gas is expelled from galaxies by interactions with hot intergalactic gas. Supermassive black holes at the centers of galaxies grow by consuming material churned up by mergers. These processes drive rapid evolution, transforming small, irregular galaxies into massive elliptical galaxies over billions of years. Galaxy clusters form through the mergers of groups under the influence of their mutual gravity. Rich clusters containing thousands of galaxies arise surrounded by hot, X-ray emitting gas. This is the normal trajectory of structure formation in dense environments. But in voids, this trajectory is blocked. The low density in voids means gravity is weak. Small structures, such as galaxies, can form because the initial density fluctuations that gave rise to them were strong enough to overcome cosmic expansion. But larger structures, such as massive galaxy groups or clusters, require more gravity than voids can provide. The density of matter is simply insufficient to pull together such massive concentrations. As a result, voids remain eternally underdeveloped. The largest structures that form in them are modest galaxy groups containing a few dozen members. Richer clusters cannot form, creating a ceiling on the development of structures. Voids become stuck in the evolutionary state that dense regions passed through billions of years ago. This filtering effect has consequences for galaxy evolution. In dense environments, galaxies undergo frequent mergers, which consume their gas and stop star formation. The galaxies become red and dead, filled with old stars, but producing few new ones. This process, called quenching, transforms star-forming spiral galaxies into passive elliptical galaxies. But in voids, mergers are rare. Galaxies retain their gas and continue to slowly form stars for billions of years. They remain blue and actively form stars much longer than their counterparts in clusters. This explains why galaxies in voids tend to be late-type spirals with ongoing star formation, rather than early-type ellipticals dominated by old stars. The filter also affects the intergalactic medium, the diffuse gas between galaxies. In dense regions, this gas is heated to millions of degrees by shock waves from galaxy collisions, and the energy released by supermassive black holes. The hot gas emits X-rays and is easily detected. In voids, the intergalactic medium remains cooler and denser, similar to conditions in the early universe. This makes voids excellent laboratories for studying primordial gas and how it gradually incorporates into galaxies. The cooler gas in voids likely contains neutral hydrogen, which can be detected by its radio emission. Surveys of neutral hydrogen in voids have revealed filamentary structures of gas connecting the few remaining galaxies, remnants of the cosmic web on a small scale. The filtering effect is self-sustaining because massive structures cannot form in voids. The void environment remains unchanged. There are no rich clusters pumping energy into the intergalactic medium. There are no massive galaxies generating strong galactic winds that expel gas. The void remains quiet and underdeveloped indefinitely. Meanwhile, dense regions continue to evolve, becoming richer and more complex. This creates a growing contrast between voids and filaments. The structure of the universe becomes more extreme over time, with voids becoming empty and filaments becoming denser. Dark energy accelerates this trend, accelerating the expansion of voids. The concept of the Great Filter has implications for life in the universe. If advanced civilizations require certain environmental conditions, such as stable galaxies with ongoing star formation, voids may be more hospitable than dense regions. Galaxies and voids experience fewer catastrophic events, such as nearby supernovae or gamma-ray bursts, that could sterilize planets. Isolation ensures long-term stability. On the other hand, the low rate of star formation in voids means fewer heavy elements available for planet formation. Galaxies and voids are typically metal-poor, which may limit the types of planets that form. Whether voids are favorable or unfavorable for life remains an open question. But if we live in a void, this could affect the galaxy we inhabit and the conditions that allowed Earth to evolve. The future of voids is increasing isolation. Dark energy is accelerating the expansion of the universe. And this acceleration has dire consequences for the distant future. As space expands faster over time, structures unbound by gravitation will drift apart and eventually lose all contact. This process is already underway, but it will intensify over the next billions and trillions of years. Voids will expand faster than the universe as a whole, as they contain less matter to resist expansion. The filaments surrounding the voids will thin as the galaxies within them are pulled further apart. Eventually, even neighboring superclusters will lose causal contact, as the space between them expands faster than light can traverse it. The fate of the universe is one of growing isolation, with structures becoming islands separated by ever-expanding voids. For galaxies within these voids, this isolation will be profound. Currently, galaxies in the KBC void can still see surrounding filaments and clusters in the distance. Light from these structures reaches us after traveling for billions of years. But as dark energy accelerates expansion, light from increasingly distant objects will never reach us. The cosmic horizon, the boundary beyond which light cannot reach us before the universe expands too much, will eventually shrink. Objects currently visible will fade from view as their light redshifts to invisibility. Galaxies deep in voids will find themselves in an increasingly empty sky with a dwindling number of visible neighbors. The cosmic microwave background, CMB, radiation will become cooler and dimmer as its photons are stretched to longer wavelengths, eventually becoming undetectable. This raises a troubling question for future civilizations. If a civilization were to emerge in a galaxy in the void billions of years from now, what would it be able to learn about the universe? Their sky would be nearly empty, save for their local group of galaxies. The CMB radiation would be too dim to detect. There would be no evidence of the Big Bang, no distant galaxies to measure cosmic expansion, no supernovae to track acceleration. They would be cosmologically isolated, unable to observe the wider universe because light beyond their immediate vicinity could not reach them. Such civilizations might conclude that they live in a static island universe, surrounded by empty space, never suspecting a vaster cosmos beyond their horizon. This scenario, sometimes called the dark future, is an inevitable consequence of accelerated expansion. Even within our own emptiness, the long-term future looks lonely. The Milky Way and Andromeda will merge in approximately 4 billion years, forming a giant elliptical galaxy, sometimes called Milkomeda. This merged galaxy will be the dominant structure in our local group. But the local group itself will become increasingly isolated. Other nearby groups, such as the Leo spur or the Virgo cluster, will recede beyond our cosmic horizon within tens of billions of years. The Milky Way will find itself virtually alone in an expanding void. Star formation will gradually cease as gases are consumed or expelled. The galaxy will dim, containing only old red stars and, eventually, only white dwarfs, neutron stars, and black holes. The night sky will darken as fewer active stars remain. On even longer timescales, trillions of years in the future, stars will become rare as their fuel runs out. Galaxies will consist primarily of the remnants of dead stars, slowly evaporating into space through gravitational interactions. Black holes will dominate, slowly growing larger as they consume any remaining material. Eventually, even black holes will evaporate through Hawking radiation, a quantum process that causes them to lose mass over incomprehensibly long timescales. The final state of the universe will be a diffuse sea of particles and radiation, eternally expanding into darkness. Voids will consume everything, and the last vestiges of structure will dissipate into the infinite expanse of nothingness. This bleak future lies billions of years away and depends on whether dark energy continues to accelerate expansion. If dark energy changes its strength or sign, the future could be different. But current observations suggest that dark energy is a cosmological constant, unchanging and inexorable. If so, the ultimate fate of the universe is the dominance of the void. The cosmic web we observe today, with its complex filaments and clumps, is a temporary phase. The true long-term structure of the universe is a void, punctuated by isolated islands of matter that become increasingly distant from one another. We live in an unusual time, when the universe still has a rich structure, and when voids are features rather than the dominant reality. In billions of years, voids will be everything. One final question remains regarding our position in this cosmic void. If we live in a cosmic void, are there other civilizations in a similar predicament? This question relates to the broader search for intelligent life in the universe. The distribution of matter influences where life can arise. Galaxies require sufficient amounts of heavy elements to form rocky planets. These elements are created by stars and scattered across space by supernovae. Gamma-ray bursts or flares can sterilize planets within thousands of light-years. Active galactic nuclei in cluster galaxies pump enormous energy into their surroundings, potentially disrupting planet formation. Voids offer a quieter environment where galaxies evolve peacefully, with stars forming at a moderate pace. Planets have billions of years to develop life, and catastrophic interruptions are rare. This may make void galaxies ideal nurseries for complex life. Lower metallicity may be offset by longer timescales available for natural chemical enrichment through stellar evolution. Arguments against voids being favorable focus on resources. Galaxies in voids are typically smaller and less massive. They form fewer stars, meaning fewer opportunities for planetary development. Lower metallicity means that the first planets to form are gas giants, with a small number of rocky worlds. Life as we know it requires complex chemistry, including carbon, oxygen, nitrogen, and other heavy elements. These elements are rare in voids. Furthermore, the isolation of galaxies in voids could limit the spread of life if panspermia, the transfer of life between star systems, plays a role. In dense regions, material ejected from one planetary system can seed another nearby. In voids, the vast distances between stars and galaxies make such transfers virtually impossible. Each galaxy in the void would have to evolve life independently. If other civilizations exist in voids, would they develop the same understanding of cosmology as we have? It's a fascinating question. A civilization in a dense cluster would observe rich structure in all directions. Their sky would be filled with nearby galaxies. They would easily detect cosmic expansion and the Hubble constant, as they could observe a large sample of galaxies at different distances. For them, the Big Bang model would be natural and quickly accepted. However, a civilization deep within the void might face difficulties. With few nearby galaxies to observe, measuring cosmic expansion becomes challenging. The influence of the void on local measurements could confuse them, leading to incorrect conclusions about the properties of the universe. They could develop alternative models that explain their observations without invoking cosmic expansion or dark energy. This raises the meta-question of whether our own cosmology is affected by our location in the void in ways we haven't yet realized. We think we understand the universe reasonably well based on observations from within the KBC void. But what if there are systematic distortions we haven't accounted for? What if the universe beyond the void looks fundamentally different from what we observe locally? Future observations extending far beyond the void will test this. If distant regions confirm our local conclusions, we can be confident that our understanding is correct. If systemic discrepancies are discovered, we may have to revise our entire cosmological model. This is a crucial test that will determine whether void dwellers are capable of adequately understanding the universe, or whether we are forever bound by our unusual location. The search for life in the universe has traditionally focused on habitable zones around stars, the detection of biosignatures in the atmospheres of exoplanets, and the search for technosignatures such as radio transmissions from advanced civilizations. Perhaps we should also consider the larger-scale environment. Civilizations in voids may be more common if voids provide stable conditions, or they may be rare if voids lack resources. In any case, the structure of the cosmic web determines where we should direct our search. If we are typical of void-dwelling civilizations, other intelligent species might also wonder whether their cosmological measurements are distorted by our location. They might also search for signals from beyond their local void, hoping to establish contact with civilizations that view the universe differently. We exist within a cosmic void 2 billion light-years wide. This is not a metaphor or a fiction. It is a fact based on observations. The KBC void is real. Its influence is measurable, and its existence challenges fundamental assumptions of cosmology. Whether it explains the Hubble strain, requires a modification of gravity, or makes our position in the universe unusual, these questions remain open. But one thing is certain: the universe is far more surprising than we imagined, and our place within it is more unconventional than we ever suspected. We are cosmic exiles, floating through a lifeless space, measuring a universe that may not be what it seems.